While the war in Ukraine rages on, both sides have been steadily improving their arsenal with newer, shinier, and more effective battlefield technology. However, there's another battlefield that may determine the outcome of this war: money. Taking out enemy vehicles and equipment was becoming more and more costly, as missiles require millions of dollars to manufacture and transport, and single-use equipment proved to be a financial burden. But that changed with the introduction of modified commercial drones. These devices can cost only a few $1,000s to create, but also cause millions in damage, and there hasn't been a cost-effective way to fight them, at least until now, and it involves the stuff of science fiction: lasers. The US has started showcasing its laser-based weapon, which aims to reduce the cost of taking down a drone from potentially tens of thousands of dollars to just $3 to $10. If the weapon proves to be effective, it could practically change the entire balance of drone warfare. But first, how have drones become such menaces in war? Over the past few decades, the armies of the world have become increasingly reliant on technology rather than sheer manpower. While the most powerful nations, at least militarily, still have substantial militaries to back up their geopolitical influence, regular soldiers might not be in the spotlight for much longer. You see, even at the turn of the 21st century, the US has shown the world what it could accomplish with drone technology. While the development of drones in battle started during World War I, the mid-2000s saw the successful deployment of the General Atomics MQ-9 Reaper deployed during the War on Terror. As a hunter-destroyer drone, the Reaper was responsible for precision strikes deep into enemy territory, leaving the opposition with no real way to counterattack. And as a bonus, the Reaper was operated fully remotely, with the pilots being hundreds of miles away. Of course, the Reaper had a huge issue that made it impractical for many militaries: a prohibitive price. It was estimated that one Reaper drone cost up to $32 million, a ludicrous price to pay for most countries. Over time, the presence of military drones waned, with the Reaper's high price tag and single-strike capabilities not being exactly what the world needed at the time. This gap in technology was compensated for somewhat by the newly made kamikaze drones, a single-use long-range drone that would deliver an explosive payload, destroying itself in the process. These designs include the Iranian HESA Shahid 136, a type of loitering munition that Iran has sold to Russia to use for its own purposes, such as the war in Ukraine that started in 2022. Shahid 136s were estimated to cost somewhere between $100,000 and $200,000. But it's suggested that Iran might need as little as $50,000 to make one. But there was another type of drone that became increasingly popular over the last decade: commercial drones. Unlike military drones, commercial drones were designed for specific, non-combat purposes, ranging from taking photos or videos to delivering items or carrying tools. Perhaps one of the most famous examples of commercial drones that have taken off, pun intended, are the drones made by the Chinese company DJI. According to Drone Industry Insights, and reported by CNBC, DJI drones currently account for more than 70% of the global drone market worldwide, and that's despite being blacklisted in the US. The main advantage commercial drones have had over their military counterparts is their affordability and ease of modifications. A single DJI drone can cost as little as a few $100s. More specialized drones, such as the DJI Mavic 3 or the agricultural DJI Agras line, cost from $1,000 to over $10,000 per unit. Still, that's considerably less than the Shahid drones. But why have commercial drones suddenly entered the spotlight? Well, the war in Ukraine has rapidly accelerated the usefulness and improvements made in commercial drones. It turns out that you don't really need a $200,000 drone to make small-scale surgical strikes relatively near your front line, some 20 to 50 miles away. Instead, you can take a commercial drone, outfit it with a larger battery, and then attach an ordnance like a bomb, mine, or artillery round to it. After that, you can let the drone fly loose, with the operator maintaining practically real-time control over the small device. Drones like the DJI Mavic could carry small grenades or bombs with a maximum payload of a few pounds. However, the larger agricultural drones could be retrofitted to carry up to 50 pounds of ordnance and batteries. These attributes have made them particularly deadly on the battlefield during the war in Ukraine. The Ukrainian army has been noted for making especially good use of commercial drones, enabling them to destroy Russian tanks or demolish fortified positions. Ukrainians have also improved on the basic agricultural drone, designing the so-called vampire drones that could carry 3 or more grenades for multiple strikes, or a large anti-tank mine for a greater area of effect. However, the Russian army isn't far behind in terms of drone usage. In fact, some Russian drone operators were so successful that the Ukrainian army had to launch specific operations to track them down and eliminate them. One such operator was codenamed Moses, a drone operator and commander who was directly or indirectly responsible for Ukraine losing 31 boats and up to 400 soldiers. When the Ukrainian military finally managed to take out Moses, it essentially allowed it to pivot into a counter-offensive against Russia, delaying the latter's offensive of the area by days. Of course, the success rate of both Ukrainian and Russian drones is abysmally low, with some Ukrainian battalions suggesting that for every drone that hits its target, up to 10 might go down before they manage to reach theirs. That's where the drones abuse their greatest advantage: economic efficiency. With the price of weaponized drone dropping as low as a few $1,000s, it's relatively cheap for either army to use drones as the first lines of attack on the enemy. But one of the few ways that drones are being taken down, through short-range missiles or anti-air defenses, can be prohibitively costly, with some of the more advanced and effective defense systems costing 10 or even hundreds of times more than the commercial drones. Using anti-air defenses only really makes sense, from an economic standpoint anyway, when taking down more expensive drones such as the aforementioned Shahids. However, both armies are practically forced to use them since there are no viable alternatives, and the damage a single drone could do can be significantly higher than the cost of anti-air missiles. A $10,000 single-use kamikaze drone taking out a tank that costs millions puts the drone operator on top, economically speaking. But that's about to change with the advent of the LOCUST laser weapon system, or LWS. The system, manufactured by the US company Blue Halo, is a truck-mounted, palletized, high-energy laser. The laser contains a separate targeting and guidance system to its left. The guidance system is almost completely AI automated. It allows the LOCUST to detect and track small flying objects, such as drones, from over 2 miles away. When the guidance system locks onto a target, the laser is powered up, creating a steady beam of high-energy photons toward the drone, concentrating their energy into a focused area and causing intense thermal heating. The increased energy manifests as heat. Given enough time and concentration of photons, the laser beam essentially melts through the drone. Depending on which part of the drone is hit or melted, there's a likelihood that the entire drone either goes up in flames, its control system shuts down, or its propellers are melted so it drops to the ground. Regardless of the method, the result is a non-retrievable drone, which is part of the reason why the weapon shows promise and why Russia or any other US enemy might need to readjust their drone warfare tactics. The laser system itself is practically platform independent. The box that houses the laser and its control system is roughly 7 feet long, 7 feet high, and a few feet wide. This allows it to be fitted onto the back of most military vehicles, and not just ground ones either. Initial experiments with the LOCUST were done using the Stryker, which could potentially allow the system to be readily deployed and redeployed near the front lines, where the modified commercial drone activity is the highest. The testing, which was done in September 2024, showed promise not only with commercial drones, but also with even more dedicated military models. According to the specifications posted by Leonardo DRS, a defense contractor that's also worked on the LOCUST system, the Stryker-mounted laser can destroy Group 1, 2, and 3 unmanned aerial vehicles. These include drones that have a lower weight than 1,300 pounds and can reach speeds of up to 280 miles per hour. The categories, which are quite broad, distinctly cover pretty much any modified commercial drone that's so far been used in the war in Ukraine. The Stryker-mounted system utilizes a Doppler radar for 360-degree visibility to aid the tracking system. The head of the laser can swivel between -30 and +90 degrees, meaning it can strike targets below the horizon line or directly above it, creating a more effective and responsive weapon. If the system doesn't use AI-powered targeting, then the Doppler radar can be combined with its high-fidelity camera to aid a human operator. To that end, the system's camera provides FPS with a 3x zoom, including an eye-safe laser rangefinder for precise tracking. The acquisition sensors operate at 120 Hz with a resolution of 1280 by 720, covering both visible and MWIR spectrums, enabling broad-field tracking of small targets. The human operation is done via a controller. This allows the soldiers to quickly get acquainted with the system being used for tracking and targeting, greatly simplifying training. Essentially, the system's operating system is designed to make the user interface and control feel as similar to a video game as possible. This allows soldiers with experience in games and exceptional hand-eye coordination to operate the laser system expertly with minimal downtime. The version of the weapon that was tested in October 2024 was reported to have a 26 kilowatt laser inside the system. However, reports by Leonardo DRS suggest that the system can be tuned to have a variable power output as low as 2 kilowatts and as high as 20 in some cases. The increased wattage directly contributes to a laser beam with more energy, which either speeds up the heating process or reduces accuracy loss over long distances. But a big part of why the system is potentially groundbreaking for countering drone warfare is its price. The initial cost of installing the system onto a platform can be relatively high, with early estimates suggesting an $8 million price tag. However, once that's done, the laser actually accepts pretty much any electrical source with batteries, generators, or even shore power configurations for ship-mounted systems, all being viable choices. After the installation, the system can practically work without any additional consumable parts, apart from batteries or recharging the coolant system. Effectively, the entire weapon is powered by electricity, and the fact that it doesn't need much makes it relatively cheap to operate directly. Based on testing, the price of spending 15 seconds to shoot down a drone could be as low as $3. Of course, this price fluctuates depending on the actual energy source that's used and how long the system takes to destroy a single drone. With that in mind, the integrated cooling system allows the laser to continuously fire for 100 seconds at a quarter cycle. This means that after those 100 seconds, it would take another 300 seconds for the system to cool down sufficiently to be used again. As such, the weapon might not be able to completely destroy a concentrated attack that uses multiple drones. Since it would take roughly 15 seconds for a single drone to be struck down, a large-scale attack could get past the weapon system and out of range. That doesn't mean there aren't any safeguards against that either. Rather than solely using the laser weapon, the striker-mounted version of the weapon system is also equipped with two traditional kinetic weapons to take down targets. The first is a 30mm autocannon chain gun, manufactured by Northrop Grumman, which is compatible with pretty much any NATO-issued 30mm round. The autocannon is similar to that found on the famous Apache AH-64 helicopters, as the base design from the latter was used in its construction. The second is a 70mm rocket launcher from BAE Systems. The rocket delivery system is specifically designed to shoot down small, fast targets, like drones, with a laser-guided system for targeting and navigation. The missile rounds themselves use proximity-fused warheads, which don't need to cleanly hit a target to detonate but will explode whenever they reach within a certain distance of the target. Of course, the fallback plan for using either the autocannon or the missile launcher is just that, a fallback plan. While the auxiliary weapon systems have already been tested to be extremely effective at taking down mobile airborne targets, there's one problem with it. The rounds that these systems use are much more consumable than the electric power that the main laser does. Additionally, the autocannon relies on a continuous stream of fire to take down targets at range, with an estimate of roughly 1 in 30 rounds actually hitting the target. This means that the price-to-effect ratio for the auxiliary system is much worse than the laser's cost-effectiveness. As a result, a concentrated drone assault, one that overwhelms the laser's initial burst, would make the system not that much more effective than any other design currently in use. Considering the relative ease with which both Russia and Ukraine have been getting their drones in the air, this scenario might not be as fictional as it may seem, and there are a few other players that might be able to help take this to the next level. The first is Iran, a country that's been steadily building up its supplies of drones, as well as sending its long-range weapons to both Russia and its allies throughout the Middle East. The second is China. As the country with arguably the largest industrial potential due to its sheer population, China has been quickly catching up to the US in terms of economic and industrial output. Additionally, a large number of the commercial drones that Russia and Ukraine have modified for their use in the war come from China and are based on Chinese technology. Due to China and Russia being allies, it's also likely that the Chinese military has been learning all it can from Russia's successes and failures in Ukraine, particularly in terms of using drone warfare to its full potential. Considering China's capacity for producing drones, it's likely that the biggest test of the newly designed anti-drone systems will be a potential China-US war, rather than the current war in Ukraine. Regardless, the weapon system itself does have a few more kinks that need to be ironed out. The first is the laser strength. Currently, experiments performed during initial testing suggested that the Locust can take out a drone in roughly 15 seconds. While this might not seem like much time, a projectile moving 250 miles per hour can cover roughly a mile in that time. As such, if the target doesn't actually go down within those 15 seconds, there's a chance that the system doesn't actually work at all and will need to fall back onto the auxiliary defenses for full coverage. For commercial drones like the ones Russia and Ukraine are primarily using, this is not such a significant problem. A Mavic drone can typically travel at speeds in the range of 40 to 50 miles per hour, at least 5 times slower than the faster Grade 3 drones according to US classifications. In 15 seconds, these drones can cover a few hundred meters at best, which is more than likely going to keep them within range of the laser. Furthermore, the strength of the laser implies that smaller drones are more likely to be destroyed in less than 15 seconds. However, that still plays into the second potential issue: weather. The laser beam is made from a stream of photons that need to reach the system's target to heat it and destroy it. However, these photons can be absorbed or deflected by larger particles in the air, These include dust, moisture, rain, or fog, and when the photons get dispersed this way, a much lower concentration of the initial laser can reach the target, leading to much lower energy efficiency and destructive power. Of course, most other weapon systems are somewhat affected by adverse weather conditions. However, lasers are uniquely disadvantaged by the fact that weather can directly reduce the accuracy, efficiency, and damage potential of the weapon. The weather problem has been spotted in tests as far back as February 2024. In these tests, soldiers weren't impressed with the initial showing of the weapons, potentially due to performing them in adverse weather conditions. As such, it's possible that the anti-drone weapons system might not be as effective during the winter months, especially in temperate or colder climates that see more rain or snow. But there's yet another issue that could make the anti-drone system difficult to use to counter faster devices: limited range. As mentioned, the current iteration of the Locust has a range of only 2 miles for its targeting and locking system, while the theoretical range of the laser is much higher. As the photons travel in a straight line until they hit something, the effectiveness of the weapon is likely going to be significantly diminished at its maximum range and beyond. This makes the Locust potentially powerful when only defending a single, vital point. Of course, with some military targets being practically invaluable, creating a stronghold around a single building is more likely to be relevant for modern warfare. However, an extended front, such as the one between Russia and Ukraine in the war, would mean that the combatants would have to field a significant number of these weapon systems to reach anywhere near full coverage. This plays into the system's high starting cost. Even if the energy that powers the laser is dirt cheap, the actual weapon is still estimated to cost around $8 million. It's unlikely that those costs will dip significantly, making a single anti-drone defense system still a relatively costly purchase for most militaries. Then you have to consider that larger front lines would likely need a comparatively high number of these devices, and the price of setting up an effective drone defense can quickly add up. Despite those drawbacks, the Locust is perhaps one of the most promising defensive systems for the newly evolved drone warfare methodologies, and perhaps due to one key aspect: speed. The Locust is likely going to be faster than conventional defensive systems in a few ways. First, the test showed that the weapons need only about 15 minutes of deployment time. This is not a particularly important aspect, but it shows that a batch of these systems can be readily moved between one location and the next to provide more coverage and a rapid response system. Secondly, the speed at which the system can disintegrate small drones is likely going to be significantly shorter than 15 seconds for smaller drones like the Mavic. If the lasers are upgraded to be more energy efficient and powerful, it's highly likely that the drone might get dropped from the air in a matter of a few seconds given a solid hit on the wing. Third, and most importantly, the actual weapon, i.e. the energy transfer, moves at the speed of light, which is impossible to replicate with conventional weapons. This means that the operator has real-time feedback on whether they're hitting the intended target. Additionally, the targeting system doesn't need to account for travel time or the drone's trajectory when firing the laser. So long as the locking system has the drone in its sights, the laser is definitely going to be hitting it somewhere. Furthermore, since the Locust is already integrated with traditional anti-drone systems, including an autocannon and a missile launcher, it's practically equipped to deal with all manner of drones. As such, the effectiveness entirely depends on the logistics and the resourcefulness of the military that's operating it. One of the key factors that might mitigate this is energy production. However, given enough batteries or generators to power the system, it could have a much higher uptime than comparable anti-air defenses such as Patriot. The fact that the laser doesn't use tangible consumables is adding another point in its favor. After all, every time the laser shoots down a drone, the enemy has to make or deploy a new one, while the system is ready to go again in a matter of seconds. Plus, the tests being done with the Locust are currently limited to ground-only applications by mounting the system on a vehicle such as the Stryker. However, it's been mentioned that the actual casing could fit on pretty much any type of vehicle. With high energy stockpile and auxiliary round demands, ships or even transport helicopters could prove to be the next perfect platforms for laser weaponry. An airborne anti-drone defense can literally take to the skies to shoot down enemy drones. However, there's even more potential in laser weapons than just shooting down drones. Laser systems have been in development for decades. The fact that they're capable of destroying drones now means that the US actually has a working prototype of a short-range laser weapon that can, in theory, melt through plastic. Given these conditions, it's not out of the realm of possibility that a larger and more powerful laser could be mounted on a ship or a vehicle and can be used to cleave through metal or make precision strikes against enemy control systems. As such, the Locust presents a possible breakthrough in military technology, as we might go from wars where soldiers fight one another to drones hunting vital targets to laser systems cleanly and efficiently cutting through equipment. While the US is among the leaders in developing such advanced laser technology, It's not the only nation to possess it. Israel unveiled its Iron Beam system as early as 2014, though it hasn't yet been deployed in active combat. Additionally, Turkey's Alka laser weapon is rumored to have been used successfully to shoot down a Chinese UAV in Libya. These advancements, alongside US innovations, naturally give pause to rivals like Russia and China. But what do you think? What does the future hold for laser weapons? Let us know in the comments, and thank you for watching. Now go and check out Russia shocked as Germany reveals never-before-seen weapon, or click this other video instead.